As a consequence of the multiplication rule for complex numbers, we also get something called, I don't exactly know how to say it, but it's French. I always say demorives rule. And demorives rule says that if I want to multiply, if I want to do like 5 times cosine 20 degrees plus 5i sine 20 degrees, if I multiply that by itself, well, it would become 25 cosine 40 plus 25i sine 40, because we multiply the two r values and add the two theta values. But that's also the same thing as 5 squared cosine times of 20 times 2 plus 5 squared I sine of 20 times 2. And with this we get a general rule, and it's a very slick rule, but here's what it is. Cosine theta plus ri sine theta to the n power can be, the answer is going to be r to the n cosine of n theta plus r to the n I sine of n theta. That's called demorives rule. And we could use it to do some questions really fast, like, I don't know, if I said 4 cosine 20 plus 4i sine 20 to the third power, I could say that's going to be 64, because that's 4 to the third. Cosine 20 times 3 is 60, plus 64 I sine 60. I could even go further if I wanted to. Cosine 60 is 1/2, so I get 32. And sine 60 is radical 3 over 2, so I get 32 I radical 3. So that's one thing I can do if it's already given in, if the number's already given in polar form. If the number's not already given in polar form, like 3 plus 2i to the 5th power, then what I could do is convert it into polar. R is square root of 3 squared plus 2 squared, which is about 3.61. Theta is tan inverse of 2/3, which is about 33.69. Be careful if you're in a different quadrant. So I could change this 3 plus 2i to 3.61 cosine 33.69 plus 3.61 I sine 33.69. Raise that to the third power. That's going to be whatever 3.61 to the third, to the 5th power, sorry, ends up being 613.1. And when I add 33.69, I multiply 33.69 times 4, I get 168.45. And my other number is the same, except it's got an I in it and a sine, 168.45. Then I could just pop into my calculator, 613 times cosine, 613.1 times cosine 168.45, and I would get negative 601. And if instead I do 613, forget the I for a second, 613 times sine 168.45, I get 128, so I get 128i. Because of rounding, I don't get the exact answer to this question, which is actually negative 597 plus 122i, but it's pretty close. The real power of demorives theorem comes from taking roots of complex numbers. Because 3 plus 2i is still 3.61 cosine 33.69 plus 3.61 I sine 33.69. But if I raise it to the 1/5 power, demorives theorem works for that also. I'm going to need 3.61 to the 1/5 power though. I do that on the calculator. I get 1.29, and 33.69 divided by 5 is going to be my angle. That ends up being 6.74. So the answer to the question is 1.29 cosine 6.74 degrees plus 1.29 I sine 6.74 degrees, which I can then pop into the calculator, just 1.29 times cosine 6.74, and I get 1.28. On the other hand, this 1.29 times sine 6.74 degrees is about 0.15. So the answer to this question is about 1.28 plus 1.5 I. So we did a lot to find the fifth root of a complex number. As an added sort of fun thing, we could say if the square root of negative 1 is I, what's the square root of negative I? Well, negative I, same thing as negative I to the 1/2 power. But negative I down here on the complex plane is actually at an angle of 270 degrees and a modulus, the R value of 1. So negative I could be written as 1 cosine 270 plus 1 times I sine 270. And when I raise that to the 1/2 power, I use demorives rule. 1 to the 1/2 power is still 1, but 270 divided by 2 is now 135. And cosine 135 is the same thing. 135 degrees is over here, so cosine is negative, so it's the same thing as negative cosine 45, just negative radical 2 over 2. And sine of 135 is actually positive radical 2 over 2. So this strange looking thing is actually the square root of negative I.